Example 33A.1. In a double-slit experiment, the distance between slits is 5 mm and the slits are 1 meter from the screen. Two interference patterns can be seen on the screen. One due to light of wavelength 480 nanometers, that's blue light, and the other due to light of wavelength 600 nanometers, that's orange light. A. Is the small angle approximation valid for the situation? B. What is the separation on the screen between the third order bright fringe of 480 nanometer light and the third order dark fringe of 600 nanometer light? Draw a picture of the situation. And then C. Do the 480 and 600 nanometer light waves interfere with each other on the screen? Explain your reasoning. Let's draw a sketch of the two-slit interference geometry and also look at the numbers for the problem. Picture-wise, I see blue light coming in, orange light that are impinging on a surface right here, and then I have a screen. So it tells us that the slits are 5 millimeters apart and that the screen distance is 1 meter from the slits. Let's put those values in. So I have my slit separation and I have my screen distance. Now let's go put in the wavelengths. The blue light has a wavelength of 480 nanometers. The orange light has a wavelength of 600 nanometers. So I got to write this into meters. So 480 nanometers is 480 times 10 to the negative 9 meters, whereas the 600 is 600 times 10 to the negative 9 meters. In A, we want to look at the small angle approximation. Now, a small angle approximation is valid up to the number of sig figs typically required for a calculation. But in two-slit interference, what you're going to find here is that a good indicator of a small angle approximation is if sine of theta and tangent of theta can be approximated by its first order term. Now this is only true here for the following situation. This is almost always true here if little d is much smaller than big D. That is, the two-slit separation versus the screen distance. If we now check that, then compare the value of little d to big D, and we could see that this is much larger than little d, so the small angle approximation is a good approximation. B. We are asked to determine the locations of the third order bright fringe of 480 nanometer light and the third order dark fringe of 600 nanometer light. What do these mean in terms of MC and MD? All fringe locations are measured from the central maximum, which is MC equal to 0. If I talk about the third order bright fringe of 480 nanometer light, when I look at the MC values here, the 0 doesn't count, so it's got to be 1, 2, 3, so that's got to be the third bright fringe from the central maximum. If now we look at the third order dark fringe from 600 nanometer light, MD0 is not the same as MC0. So this is a different location than MC0. So I have to account for the 0. So the third order then means I got 0, 1, 2, 3. So from the central maximum, it's the fourth dark fringe from the central max. Let's look at a diagram first to organize our thinking. The first thing that you want to think about here is that blue light has a shorter wavelength than the orange light, which has a longer one. So therefore the blue light should have fringes that are closer together. On the other hand, orange having a longer wavelength, the bright orange fringes should be farther apart. And that's what I'm trying to show you in the sketch here. Now if I start labeling MC here, so for the blue here, everything is measured relative to the central max. So therefore, the third bright blue fringe then is then going to be 1, 2, 3, which is the third bright fringe. But if I go to the dark fringes of the orange light, what you're seeing here is that MD equal to 0 here is not at the central max. So this 0 and that 0 are not the same, even though textbooks label them exactly the same. So then if I start to look at this thing here, then I go, the third order dark fringe, then it's going to be, I go 0, 1, 2, 3. So you could see that it's the fourth dark fringe from the central maximum. We need to calculate the fringe location. So that means the distance from here to MC equals 3, and the distance from the central to MD equal to 3. We need to identify those locations. So the height change from the 0 point to the third fringe, I'm going to call delta Y3 bright, whereas for the dark, I'm going to call it delta Y3 dark. But the question is, what is the position change from the third bright to the third dark, which I'm labeling this as delta Y in red. In other words, the difference in these two locations is delta Y, which would be delta Y3 of dark minus delta 3 of bright. Now let's go mathematically calculate these. Using the small angle approximation, the darks are MD plus 1/2 times the wavelength screen distance divided by little d, whereas for the brights, we replace it with MC lambda 480. We know that big D and little d are the same, so let's write those things and isolate them. And now I start to put in my numerical values for these guys. So for MD it's 3, for MC it's 3, I put in my wavelengths, my screen distance, and my slit separation, and this is what I get. 1.32 times 10 to the negative 4 meters, or 0.132 millimeters. That's the separation between the third order dark minus the third order bright. Do the 480 nanometer and 600 nanometer light waves interfere with each other? The answer is no. Because they have different frequencies, they will not be able to sustain any type of interference at the screen. We've already discussed the importance of the phase equation for path difference, that is phi equal to 2 pi lambda times the quantity R2 minus R1, the path difference between the two waves. I now want to go in and look at this, for example 33A.2. Let's read this example here. So I have source 1, I have source 2, there's a separation distance, and then there's a distance to a screen, which is vertically right here. So what you have then is that the sources are separated by 6 lambda, and the screen distance is 20 lambda. So what you're seeing here is that you're seeing these two waves from source 1 and source 2 that are interfering at point P here. And this height from the central maxima line is, or from the central line, is y of P. A. Conceptually explain each situation and draw a picture. At what value of yp do the rays have the minimum possible phase difference, and what is this phase in terms of lambda and pi? At what value of p do the rays have a maximum possible phase difference, and at what value for lambda and pi do you get for the phase? And then b, calculate the phase difference when y of p is equal to d. Is the resulting intensity a maximum or minimum, or is it somewhere intermediate? And if it's closer to a maximum, say it's closer to a maximum. If it's closer to a minimum, say it's closer to a minimum. Now, let's go look at that. So we need to use the phase due to path difference equation to answer these conceptual questions. So let's start thinking about this out loud. A. When does the minimum possible phase difference occur? We know that the phase is equal to 2 pi divided by lambda R2 minus R1. When is this the smallest possible value? The smallest value has to be 0. For which situation is this thing going to be 0? When R2 is equal to R1. The diagram, the only way R2 and R1 are the same here as if this point P goes up to infinity. In summary, the only way this is possible is when the path difference is 0. In other words, delta R is equal to 0, which means that y of P has to be at infinity. That means both of these rays are vertical. So the phase is then equal to 0 since delta R is equal to 0. This is the minimum possible phase. If at y equal to infinity one gets the minimum possible phase, then at y equal to 0 you get the maximum or largest possible phase difference. That means that the waves travel horizontal distance from 1 and 2 to the screen. Picture-wise it looks like this. So I have R1 in red, R2 in blue. The path difference is little d, so that's 6 lambda. So calculating the phase is going to be 2 pi divided by lambda times delta R. After plugging in delta R, the maximum phase is 12 pi. 12 pi means that I'm going to have constructive interference at y equal to 0. So in summary, I have at y equal to infinity, I have constructive interference. At y equal to 0, I have constructive interference. So therefore, in between there, I'm going to have a series of constructive interferences. How many constructive interference locations are there? Now we know that at v equal to 0, we have constructive interference. Therefore, that's at y at infinity. When phi is equal to 12 pi, we have another constructive interference, but that's y equal to 0. We know that anytime we have constructive interference, it has to follow this rule. Delta R must equal mc times lambda, but we already know that the maximum value of delta R is 6 lambda. Setting these two equal to each other, we see that mc must equal 6. So when I look at these, we know that this is the one at y equal to infinity. We know that this guy must be at y equal to 0. So between infinity and 0, I have 1, 2, 3, 4, 5 other interference patterns. So if I identify these two on the screen here, we know that mc equal to 0 is at infinity. We know that mc 6 is equal, is a question to ask is, what is the locations of these 5 maximas? 1, 2, 3, 4, 5. We use the phase difference, path difference equation. So with phi equal to 2 pi divided by lambda delta R, let's look at mc1. Delta R has to be lambda, so therefore that tells us that phi here has to be 2 pi. So if I start to look at the phases of these guys, we could see that then mc2, 3, 4, and 5 must be multiples of pi. As phi2 is equal to 4 pi, phi3 is equal to 6, 4 is equal to 8 pi, and 5 is equal to 10 pi. And then the path difference must be as follows. They have to be integral multiples of lambda. So 2 is 2 lambda, 3 is 3 lambda, 4 is 4 lambda, and 5 is 5 lambda. Put this on the screen up here, this is what we should see. Where these are all now the locations of the bright fringes in this interference pattern. If delta yp is equal to little d, what is the phase between both waves? Geometry of the setup here is that S1 is big D away from the screen. S2 is going to be D plus big D, and we could see that all of them have a vertical height of little d. So what I see here is that to get R1, I got to solve for the hypotenuse of this triangle and do the exact same thing for R2. So using Pythagorean's theorem to determine R1 and R2, I get that R1 is equal to the square root of little d squared plus big D squared. Doing the exact same thing for R2, we get the square root of little d squared plus the quantity d plus big D squared square root for R2. The phase then is 2 pi divided by lambda. Then I subtract both of these two quantities. So substituting in these values, I know that little d is 6 lambda, big D is 20 lambda. Plugging these guys in, where I now factor out the lambda, and you could see that lambda in each of these cases cancels out. This gives me in the end, you get a phase of 2 pi times the quantity 5.8. From our earlier picture, this was the interference pattern that we saw. Let's add in the phase values for these guys. So we know that at y equal to infinity, the phase is 0. And as we go all the way down here, because this is MC equals to 6, we know that this is 12 pi. Note that this phase is very, very, very close to 12 pi. So this is not at the maximal constructive interference, but it's close to the maximal interference.